So we've seen how the first derivative plays a role in whether a function is increasing or decreasing. Now we want to talk about what is concavity and what is the second derivative test. So ultimately, how does the second derivative give us information about our particular function? So first we have to talk about what is concavity. And really its first definition comes from the fact of where tangent lines lie in relation to the function itself. So if the graph of a function f lies above all its tangent lines on an interval I, then it's called concave upward on that interval I. If the function lies below all its tangents, then it's called concave downward on I. So we have two examples that I'm going to kind of show you through. The first one is going to be that case when it's concave up. So if I look at this interval from A to B and I look at any of these tangent lines, anytime I draw them, the tangent line would have to be below the curve. So the tangent lines are below the graph of the function lines above its tangents. So here f is concave upwards on this interval from A to B. What I want you to kind of recognize though is as I move along this curve, those tangent lines get steeper and steeper and steeper because of that graph being upward in shape. So ultimately the slope of these tangent lines are increasing. Well, we know that derivative plays a role with what the tangent line is, so that means the first derivative has to be increasing on this interval. So ultimately, its derivative is positive. So that means the second derivative of our function is going to be positive on this interval from A to B. And so you can see it kind of has a curved shape. That's what concavity talks about, which curve it is. You've got it curving upwards, where here it's curving downwards. So that's that main distinction between the concavity. In the second piece, no matter these tangent lines you pick, your function is going to fall below the tangent line. And you can see as you kind of come up towards that point of B, my tangent line starts to get a lot flatter. So on the interval from A to B, the function would be concave downward here. And ultimately, my slopes of tangent lines are decreasing because I'm getting flatter and flatter as I move onward in this interval. So ultimately, that means f prime is a decreasing function. So its derivative is negative on this interval. So ultimately, the second derivative of the function would be negative. Okay? So this leads to our other definition of concavity. Suppose that f is a function whose derivative f prime exists at every point in an open interval I. Then we say f is concave up on I if the first derivative is increasing over I. Likewise, f is concave down on this interval if the first derivative is decreasing. And so really the way you're going to test for concavity is you're going to figure out where is the second derivative positive and where is it negative. So this is what's known as the concavity test. So this states if your second derivative is greater than 0 on an interval I, then the graph of the original function is concave up on that interval. If the derivative is negative over the interval, then we say the graph is going to be concave down, okay? So just like we have critical numbers, which help us kind of classify our local maxes and mins, and these points correspond to that first derivative being 0 or being undefined. We have special points that occur when that second derivative changes the concavity around it. So those are going to be called inflection points. So it's slightly different because a critical number is any number that makes the derivative 0 or undefined, where an inflection point, you have to change concavity around it. So we say a point P on a curve is called an inflection point if the function's continuous there, so you can actually have a point on the curve, and you change concavity from up to down or vice versa around that point. So before you found your critical numbers and they were just anything, those could be classified as local maxes or mins. For inflection points, you're still going to find where the second derivative is 0 or undefined potentially, but you need to make sure it changes concavity around it. If it doesn't, it's not going to be inflection point. It's still important to go through that testing, but it's just not called an inflection point. So let's try an example. We're working with this function in our last couple videos. It's a nice third degree polynomial. We want to find the intervals of concavity, and we want to find those inflection points. So we have our function here. We've already found the intervals of increase and decrease on this, so we're not going to re-go over that. Our first derivative told us the information about that. So that was 12x squared plus 6x minus 6, applying that power rule. When we're dealing with intervals of concavity, we need that second derivative. So bringing the 2 down gives us 24x plus 6. So ultimately, we want to find where the second derivative is positive and where the second derivative is negative. So first, find where the second derivative is equal to 0. Or is undefined, because that is an important number as well. Okay. Fortunately for us, since this is a polynomial, it's never going to be undefined because you're never going to divide by 0. So really, we just need to see where does this actually equal 0. So subtracting the 6 gives us 24x is negative 6. Dividing by 24 really gives us negative 1/4, or negative 0.25. Okay. But now we do the same exact thing. We get that number line. We really only have this one important number, and we're testing things about the second derivative. So I have 2 intervals that I'm going to plug numbers into to see if it's concave up or concave down. So for our first interval, you can pick anything less than negative 1/4. I'll go ahead and pick negative 1. We're going to plug that into the second derivative. So that's 24 times negative 1 plus 6. So it's negative 24 plus 6. I don't care what this number is. I just definitely know it's negative. So my second derivative is negative on this interval. That tells me it's going to be curving down. So you can write concave down, and using CC to abbreviate it is perfectly fine. So on the interval from negative infinity up to negative 1/4, we are concave down. Picking a different value for interval 2, we can pick x equals 0. That's not a bad one. Plugging that in would give us 24 times 0 plus 6, so just 6. So it is definitely positive on this interval. So that would mean we have an upward shape, and it is concave up. So that interval starts at negative 1/4 and goes to positive infinity. And so since I changed concavity around this point, I can indeed call this an inflection point. Okay. If it didn't change concavity, then I wouldn't be able to do the same. So if it was negative to the left of this number and negative to the right, it's not an inflection point. Okay. But here, since the concavity switches around x equals negative 1/4, the point negative 1/4 and then the y value on the original function corresponding to that is an inflection point. Okay. And then we can use all the pieces of information that we have to get a decent graph of this. So if you go back and take a look through our video about increasing and decreasing, you remember negative 1 and 1/2 were our local max and min values. and we found other pieces corresponding to it. We had a local max at -1, a local min at +1/2, and then at -1/4, we have another inflection point. So if you want to kind of see what this graph looks like, it's concave down up until that point, and then it switches, and I have that curve up shape. So this is a rough drawing for just what that shape of our function f of x would look like. Okay. Now this leads into what's known as our second derivative test. So we have the first derivative test, which talks about local maxes and mins. Second derivative test is going to do the same thing. And so what you can kind of look at is really this is a prime example. This point is a local minimum. If you notice, it's concave up around this point. This is a local maximum. It's concave down because it's got a down cup shape. So up cup corresponds to a local min, down corresponds to a local max. So what the second derivative test tells us is suppose the second derivative is continuous near some critical number. So if f prime of c is equal to 0, so c is a critical value, and the second derivative is positive at c, then this corresponds to a local minimum value at c. If the first derivative is 0 and the second derivative is negative, then instead we have a local maximum. So we can take a look at two examples for A and for B. If we look at this value here, it is definitely concave up and it is definitely a local min. So if I go ahead and draw that tangent line in here, it is flat. So f prime of c is equal to 0. It is curved upwards. So the second derivative is going to be positive there, which means it's concave up. Likewise, for this local maximum, we have that flat tangent line at that point. So the first derivative is going to be 0. And it's curving downwards, so that second derivative is less than 0, which means it's concave down. Okay? So really you can use any of these tests to kind of classify your local maxes and mins, as long as you're comfortable with both. Your homework is going to ask you, to use the second derivative test to classify your extrema. Definitely get some practice with it. If you're not asked, though, like on a test to do something a particular way, you can kind of use whatever method you want to classify extrema. Now, realistically, we're going to be graphing all of these things, so it's going to make more sense to use the first derivative test because you're going to have to find intervals of increase and decrease. So everything's going to pretty much be done and set up for you. Okay? So let's try an example. Let's utilize the second derivative test to find local max and min values for this particular function. And the one thing you want to make known is that this does have a particular domain. Immediately, I know nothing happens at +1 because that causes me to divide by 0. So the first thing I want to do is I have to find critical numbers because those are my possible extrema. So we want to first find the critical numbers. So that's going to involve us taking the first derivative. And since it's the quotient of two things, we've got to use quotient rule. So I've got to do the low function, d high, minus high, d low, all over low, low. Okay. So cleaning that up a bit, that's 2x squared minus 2x minus x squared over x minus 1 squared, which is x squared minus 2x over x minus 1 squared. Or you can factor that out really nicely as x times x minus 2 divided by x minus 1 squared. Okay? So we need those critical numbers. And this is going to be where the derivative is equal to 0 or where the derivative is undefined. So first, in that final form that's factored, if I plug in 0, I have an issue. If I plug in 2, same thing. That's going to be important for us. And technically, if I plug in 1 as well, that causes us a bit of a problem too. So although this one makes it so that the derivative is undefined, there's not even a point corresponding to that. So there's no way this can be a local max or min. That's a vertical asymptote for this function. So although the derivative is undefined here, this isn't even in the domain. So it can't be a critical number. Okay. It's still important for us, but it's not a critical number. Okay. Now that I have my important values that can possibly be local maxes or mins, we want to go ahead and we want to evaluate the second derivative at each of these and see, is it positive or is it negative? And we're only going to test 0 and 2. 1 is not useful for us. So again, I've got to go ahead and I've got to find the second derivative. So now we need to evaluate the second derivative at each critical number. And that requires us finding the second derivative. And you can use either of these forms. This one's probably going to be a little bit easier to differentiate because if you go to take the derivative of the high in this form, you're going to have to use product rule, and that would be absolutely terrible. So instead, we get the low function. D high would be 2x minus 2. Minus high, and then D low. So that we'll have to use chain rule for. We bring that power down, decrease the power by 1 to give us the first power. And then technically you should consider chain rule because it's not just x on the inside, but the derivative of the inside is 1. And then this whole thing is divided by low, low. So you get x minus 1 squared squared again. You really have the fourth power down here. Okay. Now you can simplify this if you want to, but really you're just going to plug in 0 and 2 and you want to see the sign, so there's no point expanding all of this out. So if we plug in 0, that will give us 0 minus 1, so negative 1 squared. 2 times 0 minus 2 is negative 2. Minus 0 squared minus 0 times 2 times negative 1. And then completely divided by negative 1 to the fourth. Okay. And lucky for us, this is just going to be 0. The numerator becomes positive 1 times negative 2. The denominator would become positive 1. So overall, this thing is less than 0. So that means it has this concave down shape at that point. And so this corresponds to a local max. Okay. Now if we plug in our other important critical number, that will tell us the second derivative evaluated at 2 is going to be positive 1 squared. Then you'll get 4 minus 2, which is 2, minus 2 squared, which is 4, minus 2 times 2, which is 4, times 2 times 2 minus 1, all over positive 1 to the fourth. And so again here, I've got 4 minus 4. This is just going to be 0. The numerator ends up being positive 2. The denominator is 1. So this thing is positive. So when the second derivative is positive, it's got that upward shape. And since it's a critical number and it has this upward shape, we have a local min here. Okay. So ultimately, the local max value is f of 0, which if you plug 0 all the way in back up here, going to be 0. And the local min value is f of 2, which again, if you plug 2 back in up here, it's going to be 4 divided by 3. So the local min value is 4 over 3. So this might seem a little confusing. Your local max is 0. Your local min is 4/2 or 4/3. Why is your max smaller than your min? And it's purely because the shape of this graph. So when x equals 1, we have a vertical asymptote. We go through the point 0, 0. We go through the point 2 and 4/3, which is around here. Your graph really ends up looking like this if you were to pick some other points and plot it. So you can see this is a local max because it has that kind of shape. And this is a local min, but it's purely because that graph is split into 2 components, that we can have the local max be smaller than the local min. Okay. All right, so we've got one more example. We want to go ahead and sketch a graph that satisfies the following conditions. So we're told there's a vertical asymptote at x equals 0. Then the first derivative is positive for x less than -2. So what that means then is our function is increasing for x being less than -2. If the first derivative is negative on this interval, that means it's decreasing. Again, that's not going to be when x is 0 because that's when we have a vertical asymptote. So it's decreasing to the right of -2. The second derivative is negative for x less than 0, and that means the graph is concave down. If the second derivative is positive, that tells me my graph is concave up on that interval. Okay? So I need to draw something that satisfies all of these criterias. What I'm going to do is fill in a nice picture. I'll go out 3 in each direction. And what I tend to like to do is kind of fill in pieces of information and then draw the graph itself. So first, I know there's a vertical asymptote at 0, so I'm going to go ahead and sketch that in, and we'll do that in pink. Let's see if I can get a nicer, there we go, this should be good. There we go. So there is our vertical asymptote at x equals 0. So I know I need to hug this graph. Another important number for us happens at -2, so I'm going to kind of shade in just a little region to help me break everything up. I know on this interval for x less than -2, my graph better be increasing. Then onward, it's going to be decreasing because that's what this second criteria tells me. So I need to decrease in this interval and decrease in this portion as well. Okay. But I have to hug that vertical asymptote. Now these last two tell us concavity. So on this half, my graph should be concave down. On this half, my graph should be concave up. So I need a picture that satisfies all of these things. If we're switching from increasing to decreasing and it's concave down, that means I'm going to have a maximum at -2. So I can pick that to be really wherever I want, but I need to increase. So I'm climbing up to that point and having that downward shape. And then I'm decreasing and I need to hug that vertical line. Okay. Now over here, I need to always be concave up and I always need to be decreasing and I want to hug that asymptote. So this is one possibility for the graph of a function with these given conditions. But you have a lot more that you could draw. They'll be similar, just kind of shifted around. So we are really building up our toolkit to help us graph functions very nicely and locate all of these important quantities. What we're going to talk about next is we're going to see what happens as I let x approach infinity. So ultimately, what does long-term behavior of our function look like, and how can I possibly evaluate what those limits are going to be?